Good afternoon, dear colleagues. I'm very proud and very glad to give this talk in this mini conference devoted to Shakura's 80th birthday. And I would like to talk about our together work with X-ray nova and therefore with non-steady state accretion disk in these objects, and how we try to get alpha parameter in this disk using the models which was developed by Galina Lipunova and Nikolai Shakura 25 years ago. I will present also some historical sketch how Nikolai Shakura was involved to non-steady state accretion disks for investigate this. Konstantin Pasnov has given us very beautiful presentation how it working now, but my presentation was mainly historical. Sorry. Okay, it's working. I would like to start with the most famous paper, which was written by Nikolai Shakura and Rashid Sunyaev published in 1993 about disk accretion on black holes. And it's famous paper and the famous photos also here. And of course, immediately after publishing of this model, many people started to investigate this model in many aspects. For example, Novikov and Thorne presented the relativistic version of this model, and many people started to investigate stability of this accretion disk. And the next year, maybe in the year of the publish, this instability of the inner parts of accretion disk where radiation pressure dominates was found by Alan Lightman and Douglas Airdrie. And I'm sure that this work pushed Rashid Sunyaev and Nikolai Shakura to investigate this instability of inner parts of accretion disk, of high luminosity accretion disk. And they did it very perfect. And I would like to present shortly these results. This published in this famous paper in Monthly, theory of the instability of disk accretion onto black holes. And they found that stable accretion could be only on very specific value of viscosity in accretion disk. Of course, the real viscosity in accretion disk is not this one, and therefore, in the most part of the accretion disk, in zone A, so-called zone A, are unstable. And I would like to present this famous picture for instability branches in these accretion disks. And I put here this the basic of the stability analysis, how it looks like at the present day. So it's necessary to have some steady state solution for every values in the accretion disk and perturbate that with this kind of perturbation. And then if you contribute put this perturbated values in the equations which define this steady state solution, you can obtain dispersion relation. And using this dispersion relation, it's possible to investigate in which wavelengths the system is stable or unstable. And of course, this square of frequency, if this square frequency larger than 0, and therefore you see it will be some waves in the system. And this, if this square of the frequency is less than 0, it's not real, and therefore perturbation grows exponentially. In this case, system is unstable. But it's very interesting that Nikolai Shakura and Rashid Suleimanov did not use this standard approach and invented his own method, which completely the same in the sense, but a little bit different in the realization. It's, for my opinion, it looks like the situation when Werner Heisenberg invented matrix and matrix mechanics and operation with matrix for creating of quantum mechanics. And it's, I think it's an interesting situation for that. And as a result, they found dynamically unstable branch, this low branches here. And they found additional thermal unstable branches, much more large frequency at the same wavelengths. And they found that accretion disk are unstable if this beta parameter, radiation pressure to total pressure, larger than 0.6. It's very beautiful results, but it's not the end of the story. 10 years ago, Nikolai Shakura returned to investigate unstable disk accretion together with Yuri Lubarsky. They published a very interesting paper in Astronomy Letters in 1987. They considered this diffusion-like equation for this function. It's some parabolic partial differential equation and this component and viscous stress tensor involved and specific angular momentum. And they found self-similar solution for this function y, and they considered function of f in this form, where n and m is integers, which depend on the opacity in the matter, which dominated opacity in the matter. And they considered three cases. They considered some ring of the matter and some radius around the accreting center, or around the black holes or neutron star, and considered initial state, how matter spread to the accretion centrum. And you see it's here, this solution. Then they considered the stage where matter reached this accretion state and quasi-steady state situation arise, transition to steady state, and they also obtained this analytical solution for this situation. And at the end, they considered the final stage of the accretion of this ring of the matter, when the matter is exhausting and accretion fading, and also obtained these analytical solutions. So it's again not the end of the story, and the next return Nikolai Shakura to the unstable disk was connected with developing of X-ray observations. And in the in early 90s, modern, for that time, X-ray observatories found that there are so-called X-ray nova, and some historical nova, which was considered like classical nova. It's not classical nova, but X-ray nova as well. The most famous examples of this soft X-ray transients is Nova Monotsoritis, 1975, and Nova Morskaya was discovered by Granat Observatory in 1991. And I would like, first of all, present some results which obtained by Anna Yasinovskaya together with Ramesh Narayan and McClintock and other collaborators. They suggested the picture how accretion changes with changing mass accretion rate. If mass accretion rate is very high, therefore we see some standard alpha disk, Shakura-Suleimanov disk, and at lower mass accretion rates, some hole in the inner part of the disk appears, which fill it with very hot accretion flow, very hot gas with temperature close to virial temperature, and this hole increases with mass accretion is decreasing, and they used this classification to describe classical X-ray light curves of this X-ray nova for Nova Muscae and Nova Montserratis. And this nova has very fast rising and then exponential decay of the light curves. And Anna Isinovskaya used this approach to describe visual light curves of these two nova. And they used some irradiation as a very important thing for this problem. And they found that accretion disk has to be more thick than it was suggested by standard alpha disk theory to describe this visual accretion, visual light curves. But they used some consequence of steady state accretion disks with different mass accretion rates. To overcome this simplification, Galina Lipunova and Nikolai Shakura in 2000 published a new solution for viscous evolution of accretion disks. They considered non-stationary, non-steady state accretion disk, and they found analytical solution for this accretion disk with fixed upper, with fixed outer boundary, and these properties of this non-steady state disk was used to develop simultaneously X-ray light curves and visual light curves in these two objects, two X-ray nova. And you see here that a little bit there is some difference between theory and observations due to, unfortunately, because they did not take into account irradiation of accretion disk. And at that stage, Nikolai Shakura and Galina Lipunova involved me to this work. You see here our photos together with Nikolai Shakura's family in Constance, nearby Tübingen and in Bodensee. And here you can see me and my wife and Galina Lipunova this year. You can see how we changed it in 20 years, unfortunately. And together we considered, on the base of the solution obtained by Galina and Nikolai, considered accretion disk around Kerr black holes, and irradiation we included here, including relativistic effects. You see here how this some angular dependence of the emergent flux from inner parts of the accretion disk depends on the inclination angle, and in comparison with Newton solution. And you see here that if you observe this accretion disk face on, the flux is decreasing due to gravitational redshift. But if you observe this flux for inclined disk close to H-on situation, the relativistic Doppler boosting make flux higher than in the neutron case. And therefore, due to these relativistic effects, irradiation of the accretion disk in outer parts of the accretion disk increased in many times. You can see here the you can see here the difference. And using this approach, we computed a lot of models and tried to fit in simultaneously again X-ray light curves and visual light curves and different photometric system. And we did it using many different cases, and consider different care parameters, different alpha parameters, and so on. And you see here the solutions which we obtained. The field signs show us the situation which was coincide with estimation of mass and distance to this system at that time when this paper was published. And by red strips, I show this modern values of these parameters like mass of black holes and distance to the system. And the same we made for Nova Musca. And you see that the irradiation helped, and light curves in X-ray and in optics described very well. But what's important, we obtained very large value of alpha parameter, much larger than 0.1 for the both system and here also. And also we had to increase the half thickness of the accretion disk in comparison with standard solution, in 1.5 or even in 2 times to describe this light curves. The first problem is too high alpha parameter maybe was resolved in this work by Titarenko, Lasota, Henkel, Deus, and Siakov in Nature 2018. They assumed that there is strong wind from accretion disk, maybe magnetic wind. And due to this wind, it's possible with the same low alpha parameter make light curve of the system more steep, and therefore to reach this high steep, we make large alpha parameter to which allow to diffuse matter very fast to the accretion, to the black holes. But if we lost some of the matter with wind, it's not necessarily so high alpha parameter, and it's possible to reach this steep light curve using low alpha parameter. In concerning the second problem with half thickness of the accretion disk, we performed work together about thickness of accretion alpha disk, and here you see relative half thickness of the accretion disk for 2 cases, for very low mass accretion rays and high mass accretion rays close to Eddington limit for the 3 B, C, and A zone. Solid lines, it's my calculations, and dashed line is a analytical solution which was obtained by Galina, and of course it's the same solution like in the Shakura-Suleimanov 1973, but here using polytrope equation of state, Galina and Shakura and some student introduced some correction factor pi h, and this pi h about 2.5, and you see that from the standard theory, Hall thickness of accretion disk cannot be larger than 0.05 or 0.07. But from observations, we need some half thickness of the accretion disk into at least 1.5 and 2 times larger. And maybe this problem could be resolved using some matter above accretion disk due to wind and some clouds which arise due to thermal instability in the matter irradiated with hard X-rays. These models was suggested by Jubilee Gerardo in 2002 to explain some dips in X-ray binaries and narrow absorption line in X-ray spectra. And then in the next year, 2003, I, together with Fritz Meyer and Amy Meyer-Hofmeister, we used the same model for clouds above accretion disk to explain high reprocessing efficiency in super soft X-ray sources. And maybe these clouds above accretion disk can explain increased observed half thickness of the accretion disk in the investigated systems. So that's all what I would like to present here, and I would like to congratulate Nikolai Shakura once again and to wish him good healthness and a lot of years filled with interesting scientific work together with us. Thank you for your work, Nikolai Ivanovich, and многие лета. Thank you.